Continuing on with the Organic Chemistry 1, Chem 112 lecture series, we're going to be discussing Chapter 12, which focuses on aromaticity. So, the first thing that we have to talk about when we talk about aromaticity and aromatic compounds are benzene derivatives and benzene itself. So, benzene and benzene derivatives are aromatic compounds. Aromatic compounds contain fully conjugated pi bonds in a ring, and they have 4n plus 2 pi electrons. In this case, benzene and benzene derivatives have 6 pi electrons. Aromatic compounds like benzene are much more stable compared to non-aromatic alkenes. So here's benzene, which is the typical poster child of an aromatic compound. Benzene C6H6. And here are some benzene derivatives: toluene, phenol, anisole, aniline, benzoic acid, benzaldehyde, acetophenone, and styrene. Benzene derivatives have unique names. It's important to remember and be familiar with these common names as they're used as part of nomenclature of aromatic compounds. For example, this ring is specifically known as phenol. Take a few moments now and try to name these next two aromatic rings. Pause the video and then we'll discuss. Okay, this ring and this aromatic compound is benzoic acid, while this compound is aniline. Benzoic acid has the carboxylic acid, aniline has the amine group, while phenol has the alcohol. Now, another subclass of aromatic compounds are annulenes, which are a compound consisting of a single ring with a fully conjugated pi system. Some annulenes are aromatic. Other annulenes, despite looking planar, due to strain, some annulenes, such as 10-annuline, will adopt a non-planar conformation, and thus it is not aromatic. So for example, benzene would be 6-annuline, 10-annuline has 10 carbons, 14-annuline has 14 carbons. Another subclass of aromatic compounds are heterocycles. Heterocycles are rings containing one or more heteroatoms. Nitrogen, sulfur, oxygen, and selenium are some examples. Heterocycles such as pyridine and pyrrole are aromatic compounds. In fact, we've seen pyridine and pyrrole before, all the way back in chapter 2. Okay, continuing on, let's talk a little bit about the nomenclature for monosubstituted benzene rings. So monosubstituted benzenes are named by naming the carbon or functional group substituent and then placing benzene at the end of the name. For example, C6H5Br would be named as bromobenzene. If we have a nitro group attached to the benzene ring, this would be nitrobenzene. Likewise, if we have a 3-carbon group, which is a propyl group, how would we name this compound? Well, this would be called propylbenzene. So you name the group you name whatever group is attached to the benzene ring, and then you name benzene at the end of the name. If it's a bromine group, bromobenzene. If it's a nitro group, nitrobenzene. If it's a propyl group, propylbenzene. Let's talk about naming benzene as a substituent. In other words, let's talk about the phenyl and benzyl groups. So when the benzene ring is a substituent, the term phenyl is used for the C6H5 group. You may also see the notations of pH or the following symbol in place of C6H5. So for example, this group is known as a phenyl group, and when named as a substituent, it's called a phenyl group. So for example, this group at the 2 position would be named as 2-phenyl heptane. The benzyl group refers to the C6H5CH2 group when a group is connected to this methylene group. So this entire collection of atoms is known as a benzyl group, and the position attached to the CH2 group is the benzylic position. So for example, the following molecule would be named as benzyl chloride. Okay, let's keep going now, and let's talk about the nomenclature of disubstituted benzene rings. So when naming disubstituted benzene rings, the substituent position can be noted with locate numbers or using ortho, meta, para prefixes. So the ortho, meta, para prefixes describe the relative positions on the benzene ring. The positions directly adjacent to a given group X are called the ortho positions. The positions 2 carbons away are the meta positions, and the positions 4 carbons away are the para positions. So you can think of it as adjacent is ortho, 2 carbons away is meta, and on opposite sides of the ring are para. So for example, if we have a disubstituted benzene ring with chlorine groups at the 1 and 2 position, this could be named as 1,2-dichlorobenzene, or because the 2 groups are adjacent, this would be ortho-dichlorobenzene. By the same token, if the groups have a 1,3 relationship, this is a meta relationship, so we can call this meta dimethylbenzene. So ortho is 1,2 disubstituted, meta is 1,3, and para is 1,4. This compound would be named as para chlorobenzaldehyde because the aldehyde and chlorine group have a para relationship to one another. Let's try to practice what we've learned in terms of ortho, meta, para classification, and let's select the structures that match the indicated IUPAC name, and I'd like you to provide an alternative IUPAC name. So in this case, we have orthonitrophenol. So in this case, breaking it down, phenol means we have an aromatic ring with an alcohol, and the nitro group is at the ortho position. So this first case has a phenol with a nitro group at the ortho position, as does this molecule. This would be a meta relationship, and this molecule has a para relationship. Now, what's another name for this compound? So orthonitrophenol. You can also name this OH group as a hydroxyl group. So you can name this as 1-hydroxyl or 1-hydroxy 2-nitrobenzene. I prefer naming this as orthonitrophenol. You could also name this as 2-nitrophenol. That's another alternative name. Let's take a look at these next two cases. So I'd like you to pause the video and circle each of the compounds that correspond to the given IUPAC name. And then I'd like you to attempt to provide another IUPAC name for each compound. So pause the video, take a few moments, and then we'll discuss. So metachlorobenzoic acid. So benzoic acid means we have the carboxylic acid. And meta means there's a 1,3 relationship between the carboxylic acid and the chlorine group. That would match these two structures here. This compound has the ortho relationship. This compound has the para relationship. Another name for this compound, given that there is a 1,3 relationship, would be 3-chlorobenzoic acid. That's another name for this compound. Again, the meta relationship implies a 1,3 relationship between substituents. Looking at paraxylene, so xylene, in this case, we have two methyl groups, and para implies that they are in a 1,4 relationship. So paraxylene would be the following compound. Another name for paraxylene would be 1,4-dimethylbenzene. Because again, there's a 1,4 relationship between substituents. Okay, let's talk about the nomenclature rules for polysubstituted benzene rings. Common names such as toluene can serve as the root name. The parent substituent gets the locant number of 1 for common names. So for example, if you're looking at an aniline ring, the carbon attached to the aniline nitrogen is locant number 1. You then assign the lowest possible locant numbers to each other substituent and list substituents alphabetically with hyphenated numbers. So for example, in this case, we have a chloro group at the 2 position, a methyl group at the 4 position. So this would be 2-chloro, 4-methyl-aniline. Here are some common root names, and we can apply these root names. So looking at the following structure, we have a hydroxyl group, so this will be a phenol. The phenol carbon attached to the phenol oxygen gets a locant number of 1. Numbering around the ring to give the lowest locant numbers, we have methyl groups at positions 2 and 5. So this would be 2,5-dimethylphenol. For those curious, why didn't we number counterclockwise? That would give a locant number of 3, which is greater than that of a locant number of 2. Okay, let's keep going now, and I'd like you to try and name the following compound, which you should be familiar with as it's a pretty famous compound. Um, as a hint, we have this CH3 group, so this is a toluene base. We have nitro groups at positions 2, 4, and 6. So this is 2,4,6 trinitro toluene, also known as TNT. Yes, that TNT. This is an explosive compound. Okay, let's continue on with this practice, and I'd like you to try naming the following two compounds. So please pause the video, and then we'll discuss momentarily. So in this case, we have this aldehyde. So this is a benzaldehyde. So in this case, numbering to give the lowest locant numbers, this would be 5-bromo, 2-methyl benzaldehyde. Looking at this next compound, we have this methoxy group. So this would be anisole. Yep. Numbering, we have the iodine at the 2 position. So this would be 2-iodoanisole. So this is why I encourage you to be familiar with the common names for common aromatic compounds, as it makes naming so much easier. Okay, let's now discuss a little bit about benzene's structure and stability. Benzene is planar hexagonal with carbon-carbon bond angles of 120 degrees. The benzene carbons are sp2 with each of the p orbitals fully conjugated in the pi system. Because the pi electron density is delocalized across all atoms in the ring, the electron density in all 6 carbon-carbon bonds is identical, and that's why all carbon-carbon bonds are the same length of 139 picometers. Note, these bonds closely resemble quote-unquote 1.5 bonds, as they have the bond length and strength in between that of a double and a single bond. Further, as a consequence of the fact that all of the pi bonds are fully conjugated, the carbon-carbon double bonds in benzene are more stable and less reactive than a typical alkene. Benzene rings react via substitution rather than addition reactions common for alkenes. Additionally, to get a benzene ring to react, you often have to use a catalyst and higher temperature, more vigorous conditions in order to provoke the benzene ring to react. Now, based on heat of hydrogenation, benzene is about 150 kilojoules per mole, more stable than expected for an isolated alkene. Benzene is much more stable than comparable conjugated alkenes. So there's something special about the fact that all of the pi bonds in the benzene ring are fully conjugated. There's something special about aromatic compounds. So one way that we can explain benzene stability is using molecular orbital theory. So when p orbitals overlap to form a pi system, molecular orbitals are generated equal to the number of conjugated p orbitals combined. For each bonding molecular orbital, we generate an antibonding molecular orbital. So for example here, if we have our 2 p orbitals, we get a bonding MO and an antibonding MO. As orbital energy increases, the number of nodes increases, starting from 0 nodes. A node is a region with no electron density, and nodes are placed symmetrically on or between atoms. What does a node look like? Right here. Here is a node. As you can see, there's no electron density in this region. Notice as we go up in energy, we increase the number of nodes that we see. Now, part of the reason why benzene is particularly stable is that if we take the 6 p orbitals in benzene and we generate 6 molecular orbitals, we generate 3 bonding orbitals with the 6 pi electrons and 3 antibonding orbitals with no electrons. The other thing that I'd like you to note in particular for benzene is that because the entire pi system is present in a fully conjugated set of orbitals arranged in a ring, you end up with multiple orbitals of the same energy. These are known as degenerate orbitals. Now, because benzene specifically has 6 pi electrons, these 6 pi electrons end up occupying these bonding molecular orbitals in a lower energy state compared to if these electrons were just in isolated p orbitals or even isolated pi bonds. Benzene is especially stable and considered an aromatic system since its bonding orbitals are completely full and its antibonding orbitals are empty. This is known as a closed shell system. These kinds of closed shell systems, where your bonding molecular orbitals are completely full and your antibonding molecular orbitals are empty, are especially stable. So if there's anything I want you to take away from this, is that this closed shell system is very stable. And these pi electrons are very stable. They're in a lower energy state compared to if they weren't conjugated. Okay, so aromatic compounds are especially stable. How do we know if a compound's aromatic? Well, there's a general set of rules that were developed by Huckel, which states that a ring system is considered aromatic if the compound contains a planar ring containing a pi system of fully conjugated p orbitals. So the ring must be planar, flat, and it has to have a pi system of fully conjugated p orbitals. Further, the ring must contain 4n plus 2 pi electrons. So what that means is if n is a number, it must contain 2, 6, 10, and 14 and so forth pi electrons. Aromatic rings are very, very stable. Why are they stable? Aromatic systems are stable as their bonding molecular orbitals are full and their antibonding molecular orbitals are completely empty. Examples of aromatic systems include benzene and the cyclopentadienyl anion. As you can see, both of these systems have 6 pi electrons and thus follow the 4n plus 2 rule. Now, a counterpart to aromatic compounds are antiaromatic rings. A ring system is considered antiaromatic if the compound contains a planar ring containing a pi system of fully conjugated p orbitals, and the ring contains 4n pi electrons, be it 4, 8, 12, and 16 pi electrons. Antiaromatic systems and antiaromatic rings are not stable. Antiaromatic rings are unstable and reactive. Their carbon-carbon double bonds react closer to isolated alkenes. Antiaromatic molecules, such as, for example, cyclobutadiene, which has 4 pi electrons fully conjugated in a ring, antiaromatic molecules will distort bond lengths or molecular shape to minimize conjugation. For example, cyclobutadiene, it's hard to isolate on its own because it readily will react with itself to break aromaticity. Additionally, cyclobutadiene adopts these distorted bond angles and bond lengths to minimize conjugation. So rather than matching its theoretical square shape based on the carbon-carbon bond lengths, cyclobutadiene has a distorted shape, in part to minimize conjugation. Cyclooctatetraene, which is another compound that looks antiaromatic but isn't, cyclooctatetraene adopts a distorted non-planar geometry to minimize p orbital overlap. So anytime a molecule is antiaromatic, anytime it has a ring containing 4n pi electrons fully conjugated in the ring, you're going to see that the molecule will typically adopt a distorted shape in order to minimize or break conjugation. So aromatic compounds, very stable. Antiaromatic compounds, very unstable. Now, how do we explain that? Well, to do that, we're going to need to talk a little bit about molecular orbital theory and Frost circles. So when p orbitals are combined to yield bonding and antibonding molecular orbitals, the bonding and antibonding orbitals are arranged symmetrically about zero energy. To effectively draw the relative energies of each bonding and antibonding molecular orbital, we use a Frost circle. So in this process, you're going to draw a circle. You're going to draw your ring inside the circle with one vertex pointing down. So one carbon needs to be at the bottom. You're then going to draw a horizontal line representing a molecular orbital at each point the ring and circle intersect. You're going to draw a dotted line through the center of the circle, and then you erase the ring and circle. All bonding molecular orbitals are below the line, while all antibonding molecular orbitals are above the line. Non-bonding molecular orbitals on the line are seen for antiaromatic rings. This looks complicated, but in practice, it's quite simple. So here's benzene. If you draw the Frost circle, so you draw a circle and you draw your ring. So here's the circle. At each point in the ring, you draw a line noting the position of a molecular orbital. You then draw a dividing line down the middle. On top are antibonding molecular orbitals. On the bottom are the bonding molecular orbitals. For cyclobutadiene, as you can see, it is anti-aromatic. And as you can see, in addition to bonding and antibonding, we have a pair of non-bonding molecular orbitals. Here are some sample MO diagrams for various aromatic rings. And once you create your molecular orbital diagram, you can then fill that diagram with your pi electrons. So let's do an example of this. So here we have the cyclopentadienyl anion. So here I'm going to draw my ring. And I'm going to draw my ring so one carbon, one vertex of the ring is pointing down. From here, I'm going to draw out the circle. Next, at each point where the ring and circle intercept, I'm going to draw a line. I'm going to divide my molecule symmetrically, at least as symmetrically as possible. From here, we have our pi star, antibonding, and our pi bonding. To redraw the MO diagram that I've prepared, I can now fill it with our pi electrons. I have 6 pi electrons, 1, 2, 3, 4, 5, 6. So as you see, this compound is clearly aromatic. It has full bonding molecular orbitals, but an empty antibonding set of molecular orbitals. I'd like you to apply what you've learned now, and I'd like you to draw an MO diagram for the following cation. This is a pretty unique cation, and I'd like you to tell me whether it's aromatic or anti-aromatic. So let's discuss. So in this case, we're going to draw our ring. We're going to draw the Frost circle. At each point where the ring and the circle intercept, we draw a line. So here we have the pi star and pi molecular orbitals. we have 2 pi electrons, so this is an aromatic compound. And we can see that based on the fact that the bonding molecular orbital is filled while the antibonding molecular orbitals are empty. Wonderful. So let's talk now about antiaromatic systems and molecular orbital theory. So the highest occupied molecular orbital is the highest energy orbital containing electrons. The lowest unoccupied molecular orbital is the lowest energy orbital without electrons. Antiaromatic systems are unstable since their highest occupied molecular orbitals are half full. It's known as an open shell system. Further, antiaromatic systems place their highest energy electrons into non-bonding molecular orbitals. Often, these highest energy electrons are also unpaired in the MO diagram for antiaromatic systems. So, because of this quote-unquote open shell arrangement, antiaromatic systems are particularly unstable because they have half-filled, partially occupied, non-bonding molecular orbitals. So, I'd like you to tell me whether each of the following ring systems is aromatic or antiaromatic, or neither. So in this case, this compound is not conjugated. So it's neither aromatic or antiaromatic. As a reminder, an aromatic system follows 4n plus 2 pi electrons fully conjugated, while anti-aromatic systems have 4n pi electrons. With this in mind, take a look at these next 2 ring systems and tell me whether they're aromatic or anti-aromatic. So pause the video, work through these examples, and then we'll discuss. So in this compound, we have 2, 4, 6, 8, 10, 12. So 12 pi electrons, that follows the 4n rule. So this would be anti-aromatic. This next compound has 2, 4, 6, 8, 10, 12, 14. That's 4n plus 2. So this would be an aromatic system. Let's now approach these next examples using a more rigorous definition of aromaticity. So in this case, I'd like you to tell me which of the following systems are aromatic or anti-aromatic? And I'd like you to answer the question, which of the following rings are more stable? And I need you to draw an MO diagram to justify your answer. So take a few moments to work through this problem. Pause the video and we'll discuss momentarily. Okay. So in this case, we have 6 pi electrons. Well, in this molecule, we have 4 pi electrons. This compound would be aromatic. This compound would be anti-aromatic. To justify this, we're going to need to draw in an MO diagram. We've already seen this 5-membered aromatic ring before. Here's what the basic MO diagram looks like. Again, derived from the Frost circle. And we have 1, 2, 3, 4, 5, 6 pi electrons. Looking at the 3-membered ring with an MO diagram that looks like this, here we have 1, 2, 3, 4 pi electrons. So we have a half-filled set of highest occupied molecular orbitals, and this is unstable. So as we can see, the compound on the left would be more stable as it's an aromatic compound. The compound on the right is very unstable because it's an antiaromatic ring. It has a half-filled, highest occupied set of molecular orbitals. Okay, let's talk a little bit about antiaromatic systems and non-aromatic systems. So antiaromatic compounds are unstable. Cyclobutadiene has distorted bond angles and it reacts readily, in part because it's antiaromatic. Small ring systems, 6 carbons or less, cannot easily distort their molecular shape. However, when we get to large ring systems, 7 carbons or more, such as cyclooctatetrene, large ring systems can adopt distorted, non-planar geometries to minimize p orbital overlap. As cyclooctatetrene is non-planar and its p orbitals are not conjugated, it's known as a non-aromatic compound. As you can see, because this molecule adopts a distorted non-planar geometry, the p orbitals are not conjugated and this molecule is non-aromatic. Now, why do we care about this distinction? Well, non-aromatic compounds like cyclooctatetrene are relatively unstable as a result of their distorted shape and geometry, albeit not as unstable as an antiaromatic compound. The pi bonds in cyclooctatetrene react in addition reactions like a typical isolated carbon-carbon bond. So you can think of the pi bonds in a non-aromatic compound just like any other garden variety alkene pi bond. It reacts in all of the same alkene reactions without anything special. So when you have large rings that are containing 4n pi electrons, these large rings will often distort and bend out of the plane and adopt distorted geometries to break conjugation. These larger rings are typically going to be non-aromatic. They are neither aromatic nor antiaromatic. They've broken their planar geometry. They adopt a distorted shape. Their p orbitals are not conjugated, and so they react like any typical non-aromatic compound. Their pi bonds react like a normal isolated alkene. Okay, let's now talk a little bit about aromatic heterocycles. So heterocycles are rings containing one or more heteroatoms. Nitrogen, sulfur, oxygen, and selenium are some of the common ones. Heterocycles such as pyridine and pyrrole are aromatic. In pyridine, the lone pair is localized, while in pyrrole, the lone pair is delocalized. Why? In pyrrole, the lone pair is held in a p orbital, while in pyridine, it's isolated and held in an sp2 orbital. This is important. Part of the reason why pyrrole is much less basic than expected is because protonation breaks aromaticity. You have an aromatic base, and this compound is not aromatic. Because when you protonate, you no longer have 6 pi electrons fully conjugated. Protonation breaks conjugation. By this notion, formation of an aromatic compound is very favored. If a step breaks aromaticity, it is not favored. That's why pyrrole is a weak base, much weaker than would be expected. Because if you protonate pyrrole, you break aromaticity. By the same token, I'd like you to note that this compound is a strong acid because deprotonation would make an aromatic product. So I'd like you to tell me which of the following compounds is a stronger base, pyrrole or just this normal cyclic amine? based on just what I've presented to you, this cyclic amine is a stronger base, in part because you don't have this huge penalty for protonation where you break aromaticity if you protonate pyrrole. So pyrrole is a weaker base than this normal cyclic amine because if you protonate pyrrole, you pay this huge penalty as a result of breaking aromaticity. Let's now talk about aromatic ions. The 4n plus 2 rule and rules regarding aromaticity apply to ions as well as neutral species. Ions can be aromatic. For example, the cyclopentadienyl anion and the cycloheptatrienyl cation are aromatic. Both ions contain 4n plus 2 pi electrons in a planar ring of continuous p orbitals. So this has 6 pi electrons. This compound has 6 pi electrons. The cycloheptatrienyl cation is also known as the tropylium ion, as we've seen this ion previously in our discussions of mass spectrometry. In terms of aromatic ion stability and conjugate acid acidity, formation of an aromatic conjugate base anion is very favored, and this makes the parent acid very acidic. For example, cyclopentadiene has a pKa of 16, and it's unusually acidic, in part because deprotonation gives an aromatic anion. So if you deprotonate cyclopentadiene, this anion, the cyclopentadienyl anion, is aromatic. In general, aromatic ions and compounds are especially stable and are more easily generated. As a corollary, anti-aromatic ions and compounds are especially unstable and are difficult to generate. So with that in mind, I'd like you to predict which of the following protons are more acidic. And as a hint, I would suggest you draw the conjugate base anion. So pause the video and then we'll discuss. So in this case, if we look at the conjugate base anion, here are the two conjugate base anions. Looking at the compound on the left, we have 8 pi electrons. So this anion is anti-aromatic. For the compound on the right, we have 6 pi electrons, so this is aromatic. Because it is far easier to generate an aromatic conjugate base by deprotonation, this parent acid is going to be more acidic. And specifically, this proton is going to be more acidic. The key point, if you can generate an aromatic conjugate base, that makes the parent acid more acidic. If you're trying to generate an anti-aromatic conjugate base, that makes the parent acid less acidic. Aromatic ions are easy to make, anti-aromatic ions are hard to make. Okay, let's talk about another factor and another consideration. When we talk about aromaticity, aromatic ion formation can play a role in specific SN1 and E1 reactions. So because aromatic ions are especially stable and are more easily generated, reactions that generate an aromatic cation are accelerated. So for example, if we're looking at which of the following substrates reacts faster via an SN1 reaction, if we take a look at each of these two cations, so I'm going to label these options A and B. For compound A, we'd make the following cation. which has 6 pi electrons and is aromatic. So it's very easy to make cation A. By comparison, cation B is conjugated, but it's not aromatic. So because cation A is easy to make, compound A will have a faster SN1 reaction. So it's easy to make aromatic ions. That's the key point. By the same token, antiaromatic ions are especially unstable and are difficult to generate. Reactions that generate an antiaromatic cation are not favored and may not occur. So to apply what we've learned, I'd like you to tell me which of the following substrates reacts faster via SN1 reaction, and I'd like you to draw the cations to justify your answer. So pause the video, take a few moments to work through this example, and then we'll discuss. So compound A generates the following carbocation. This should immediately set off alarm bells as this has 4 pi electrons, and this is an anti-aromatic cation. What that means is forming this cation is going to be slow. So even though compound B, we're just making a secondary carbocation, compound B is going to have the faster rate of SN1 reaction just because we're not having to fight this giant uphill battle to make an anti-aromatic cation as we see in compound A. Compound A may not even react at all via an SN1 pathway and may intend to actually prefer to do an SN2 reaction. This really highlights the huge penalty that you have to pay to make an anti-aromatic cation or anion. Anti-aromatic compounds really are that unstable and hard to form. Let's talk about aromaticity in the context of elimination and tautomerization. Elimination reactions that generate aromatic products are accelerated, while elimination reactions that generate anti-aromatic products are not favored and may not occur. For example, which of the following compounds will have the fastest rate of elimination? Well, if we eliminate this chlorine atom, we get benzene, which has 6 pi electrons. This is an aromatic compound. By comparison, for our second compound, if we eliminate our halide, we get an anti-aromatic compound. As it is easy to form aromatic compounds and very difficult to form anti-aromatic compounds, A will have the faster rate of elimination. To apply what we've learned, I'd like you to tell me which of the following compounds will have the fastest rate of elimination. So pause the video, take a few moments to discuss, and then we'll discuss this example momentarily. Okay, so just like before, let's look at the two products. So A, elimination, yields this pretty unexciting diene, neither aromatic nor anti-aromatic. Compound B, on the other hand, is a little bit problematic in that elimination in compound B yields cyclooctatetrene, which has 8 pi electrons and would be considered anti-aromatic if it wasn't non-planar. Because compound B is unstable, in part because it has a lot of anti-aromatic character, it is far easier to form and eliminate with compound A. So compound A will have the faster rate of elimination, in part because we're not paying this penalty to generate a compound that has a large amount of anti-aromatic character. One last place where aromatic and anti-aromatic considerations come up is in this idea of tautomerization. In general, the aromatic species is formed over the non-aromatic or anti-aromatic species. Because tautomers are structural isomers that can be interconverted via proton transfer, the aromatic tautomer is favored and rapidly generated. So for example, here are the two tautomers of phenol. Which one of these tautomers is more stable? The aromatic tautomer. You don't see any of this ketone tautomer of phenol. Why? This compound is aromatic. This compound is non-aromatic. No competition at all. One thing that we often can note as a side effect of aromatic and anti-aromatic considerations is that you can often see compounds that, so when we look at compounds where there is a resonance structure or possible way that we can draw the compound to make it an aromatic compound or aromatic ion, you will often see that that aromatic structure will have a huge contribution to the observed structure for your molecule. In other words, if a structure can generate a cationic or anionic resonance structure that is aromatic, that structure will have a greater contribution to the resonance hybrid. This can be seen in the bond lengths in the structure and the cationic anionic character at atoms in the structure. So for example, if we're asked which of the following resonance structures is a major contributor, and we see in this case, this is a non-aromatic compound. And in this case, we have a 2-pi electron system, an aromatic system. This resonance structure is a major contributor. So what this means is if we look at this carbon is going to have a large amount of cationic character, much more than usual, because this resonance contributor is a major contributor. Why? Because this resonance contributor is aromatic. It's the same reason why, if we look at on the right, this ring has 6 pi electrons. So this contributor is a major contributor to your actual structure. What this means is this carbon-oxygen double bond has a lot more single bond character and is a lot more polarized than usual because this contributing resonance structure plays a much bigger role into the actual structure that we observe. It's a major contributor because it is an aromatic structure. Now, how does this come up in terms of observable reactivity? This can explain why carbons are more or less electrophilic than expected. For example, cyclopropanone is less reactive. So cyclopropanone is less reactive than cyclopropenone, as the carbonyl carbon in cyclopropenone has less cationic character. So let's take a look at what's happening here. So here, if we look at this contributor, this is cyclopropenone with the alkene. And if we compare to cyclopropanone, the main difference is if we look at this contributor, this resonance contributor is aromatic. And as a result, in our actual structure, this carbon is going to have more positive charge. Because this aromatic structure, this aromatic resonance structure, is a major contributor. By comparison, in cyclopropanone, this is non-aromatic. And as a result, the carbonyl carbon in cyclopropanone has less cationic character. So, this also can explain why the CO bond in cyclopropanone is shorter and stronger, as it has more double bond character. So whenever you have an aromatic contributing structure, that has a greater impact on the observed bond length, strength, and charges observed in the resonance hybrid. Because in cyclopropanone, we have a contributing structure where we have this aromatic contributing structure where there's a lot of positive charge on carbon, and this carbon-oxygen bond is longer. In the actual structure, in cyclopropanone, there will be a lot more positive charge on carbon. This carbon is much more reactive, and this CO bond is longer, has a lot more single bond character. Compared to in cyclopropanone, where this resonance structure is non-aromatic and minor, the carbonyl carbon will have less cationic character, and this CO bond is shorter. One last thing that we have to talk about in terms of aromaticity is this idea of polycyclic aromatic compounds. So polycyclic aromatic compounds are aromatic compounds that have rings that share a set number of carbon atoms. These are known as fused rings. Compounds from fused benzene or aromatic heterocyclic rings are they themselves aromatic if they contain 4n plus 2 pi electrons. For example, naphthalene has 10 pi electrons, anthracene has 2, 4, 6, 8, 10, 12, 14 pi electrons, and so forth. Polycyclic aromatic compounds are pretty unique and interesting compounds, but we're just going to discuss them as a footnote as we conclude this chapter. So that concludes our discussion of benzene aromatic compounds and aromaticity, and we'll be continue on with this lecture series with chapter 13, which focuses on reactions of aromatic compounds.